Today we're going to talk a little bit about power and root functions. We've already briefly went through examples of this when we looked at f of x equals x squared parabola, or back when we were learning first all the little functions like f of x equals x squared, f of x equals x cubed, f of x equals square root of x, f of x equals cube root of x. We learned about those basic functions. But now we're going to expand on that and have not just 2 or 3, but have other numbers as well for our exponents or our indices. Starting with power functions. A power function is a function of the form f of x equals x to the b, where b is a constant. So in other words, you have x raised to some exponent, and then that's a power function. And what you're going to have to be able to do with power functions is evaluate them and also be able to sketch graphs. So let's first look at an example where we're going to be doing some evaluating. Let's say you have the power function f of x equals x to the negative 0.71. Okay, so your power up here is some constant. It doesn't have to be an integer. It can be a fraction or decimal, but it can be an integer too. And they want us to evaluate this where x equals 3.8. Okay, so you're finding f at 3.8. So we got 3.8 raised to the negative 0.71. Now at the negative exponent, I know that this is equivalent to 1 over 3.8 to the positive 0.71. But beyond that, I don't know how to do this by hand. There's all kinds of tables you can use, and there's techniques, but we don't need to worry about that for this class. What we can do is go ahead and put it into calculator. Pull up my calculator. Okay, so in the screen here, we can say 1.2. And then for the exponent, use this little caret symbol. And then I'm going to put it in parentheses just to make sure everything is clear. Oh, not 1.2. Sorry about that. I keep glancing at the wrong problem. 3.8. Whoa. Raised to the negative 0.71. Yeah. All right, so the little caret gives it the exponent, and the exponent is negative 0.71. Hit enter, and there's your value. If you want to approximate to the nearest hundredth, you would round it to 0.39. So there's your power. So you can say that it's approximately 0.39. All right. Another example, you don't have to just have a single x to a power. You could have something like this, where you have x to the 5/4 minus x to the negative 3/4. 5/4 means you're doing the fourth root and raising that to the fifth power. Negative 3/4, it's 1 over x to the 3/4, but you're doing the fourth root and cubing. And they want us to figure this out, f at 7. I mean, I could rewrite this and say, well, I know that 7 to the negative 3/4 is the same thing as 1 over 7 to the positive 3/4. But beyond that, not a whole lot I feel like I can do right now. I don't know what the fourth root of 7 is. It's a decimal of some kind. And I could extract the root by hand, but I learned to do that back in 7th grade, and I can't remember anymore how to do it. And, when you have calculators, who needs to? So what I can do instead is put this right into the calculator. Okay. So I've got 7. You know what? I'm going to put this in parentheses. 7 raised to the 5/4 Whoa, how did I end up with 2 carats there? I don't need 2 carats. There we go. 7 raised to the 5/4 minus 7 raised to the negative 3/4. And there you go. So if you want to round to nearest hundredths place, you'd round it to 11.15. Okay, so that's a little bit about putting values in to one of these power functions. If you want to graph a power function, you can use some of the same techniques you've used in the past with graphing, where you can come up with some x values, plug them in, see what your y values are. For example, let's say you have f of x equals x to the 1.5, and you want to graph that. We're going to graph this where x is greater than equal to 0. Okay, so they told us go ahead and use x greater than equal to 0. So I'll go ahead and start with 0. If you put in 0 to the 1.5, you're going to get 0. I'll try putting in 1 to the 1.5, you're going to get 1. You know, put in some other values. You want to put in enough values to get a really good idea of what the curve looks like. If you don't put in enough, then it's hard to tell. So what if we put in 2? Let's see. 2 to the 1.5. Go ahead and use your calculator. I'm not going to switch over right now. I'm just going to use a calculator here in my hands. But you can go ahead and do a calculator on your own and get the same thing. I got around 2.83 if I'm doing it to nearest hundredths. Close enough for graphing, right? If I put in a 3, that's 3 to the 1.5. That's going to be approximately what? Let's see. 5.20 if you round to the hundredths place. Let me go a little further out. Let's put in a 6. Just want to get a good idea of how the curve's going. I get 14.70. That's a little that's off of my chart, off of my grid here. So I can go up to 11 and the 12's at the very tip top there. So maybe we'll try 5. See what that looks like. 11.18. So that I can actually put on my grid. All right. And why did they say x greater than equal to 0? Wouldn't we try to put in negatives? Well, 1.5 is the same thing as 3 halves. An exponent of 3 halves, the bottom number 2 tells me I'm doing a square root, and the top number 3 tells me I'm cubing that answer, that result. Well, square roots, the square root of x, the domain is 0 to infinity. So we're restricted by that domain, that real domain. So we have to start with 0 and go higher. All right, 0, 0 goes here. 1, 1 goes here. 2, 2.83 can go roughly here. 3, 5.20 can go about right there. 5, 11.18. Go roughly right there. And 6 is 14.70 is way off. So now we know what it's supposed to look like. And you could get some more points in between to get even a clearer picture of the curve, but that's close enough. It keeps going. So there you go. Let's put it in the calculator. Take a look at it in the calculator. Y equals, that was x to the 1.5. We hit graph, and it shows the same thing. Shows that nice like half parabola shape going up there. It just confirms what we were already doing. All right. So you're going to have a little bit of fun with evaluating. You're also going to have a little bit of fun with graphing. And they're also going to throw at you some word problems. So let's do a word problem real quickly together, just to deal with power functions. So it says, suppose that the wingspan, L in feet of a bird weighing W pounds is given by L equals 2.43 W raised to the 0.3326. So scientists have done all kinds of measurements of all kinds of birds, and L represents wingspan in feet. W represents the weight in pounds, of a bird's weight in pounds. So they've taken lots of measurements of birds between their weight and their wingspans. And they were able to figure out that they could model the wingspan length of a bird based on its weight using this function right here. L equals 2.43 times W to the 0.3326. This function reflects the data they've collected as they've looked at all kinds of birds, all different shapes and sizes of birds. And we can then make some predictions about, like, we can estimate a wingspan of a bird knowing its weight. Or if you know its wingspan, you can estimate its weight. You can go either way. But we have this nice power function here. So because we have input variable W raised to a power, and then times by that factor of 2.43. Okay, so then let's say we want to estimate the weight or the wingspan with a weight of 5.2 pounds. So we're going to take 2.43 times, and then it's the weight in pounds, so 5.2 raised to the 0.3326. All right, so you got to follow your order of operations. You got to do the 5.2 raised to the power times 2.43. I'll go ahead and put that in my calculator here so you can see. Now the calculator will do order of operations. So I can go ahead and put in 2.43 times, and then I'm doing 5.2 raised to 0.3326. Hit enter, and there we go. And I'm going, I think it's rounding to the nearest tenth, so the wingspan is roughly 4.2 feet. So that's an example of an application problem or a modeling problem where the model has this function that's a power function, and then you can use it from now on to work with other specimens that, like, if you're a scientist out in the field. All right, next. Where there's powers, there's also roots. A root function is a power function where your exponent is a fraction, 1 over n, where n is some integer 2 or higher. So like x to the 1/3, x to the 1/4, x to the 1/2. You know. And if you have a fractional exponent, remember the denominator in the fraction is your index. And then the numerator, it doesn't have to be 1, it can actually be something else. Then that's which power you're raising to. The domain of a root function includes all the real numbers that can be substituted for x and still produce a real result. We're interested in real answers, not imaginary. If the index is 2 or higher and even, you would set the radicand greater than or equal to 0 and solve to figure out what your domain would be. If your index is 3 or higher and odd, the domain automatically includes all real numbers. Okay, for example, let's say you have a function f of x equals square root of 9x plus 18. Okay, that's the same thing as saying 9x plus 18 raised to the 1/2 power. Those two are one and the same. And you're interested in finding the domain. So you're interested in figuring out what values can you plug in for x and get real results back for y. You know, you're trying to figure out what all numbers are allowed to be plugged in here. Or if you're graphing it, what all x values will be included on the graph. Well, if it's a square root, a fourth root, a sixth root, an eighth root, if you're looking at the index there and it's even, in this case it's square root, so the index is 2, then you take whatever your radicand is, the part that's under the radical sign, and you set it greater than or equal to 0. Because you're saying, I want to take the square root of something non-negative. I don't want us to take the square root of a negative because then I'll go into imaginary numbers. So I've got 9x is greater than or equal to negative 18. X is greater than or equal to negative 2. So my domain in this case is from negative 2 to infinity. And if I go to graph this thing, the graph's going to start at negative 2 and take off. So the domain will be from the negative 2 here out to infinity out here. Now if you have something like f of x equals fifth root of x plus 32, looking at that index, it's odd. Automatically your domain is going to be negative infinity to infinity. If it's a cube root, a fifth root, a seventh root, that's your domain's automatically going to be negative infinity to infinity. Because you have, with those, you have a curve that looks like this. So it extends forever to the left, forever to the right. So that's why the whole negative infinity to infinity. Let's see. And then let's do one more for the domain. F of x equals square root of 81 minus x squared. Let's see, 81 minus x squared has to be greater than or equal to 0. Notice that we have a quadratic inequality here. Let's see, where does 81 minus x squared equal 0? So you can factor this one. So you can avoid going through the quadratic formula because this will factor. You do have a difference of squares here. Two values where it equals 0. If you look from negative infinity to negative 9, You can plug in, let's say you plug in -10. You do that, you're going to get a negative result. If you look between -9 and 9, let's say you plug in 0, you're going to get a positive result. And then something from 9 to infinity, plug in 10, you get a negative result. So where is it greater than or equal to 0? Well, right here it's greater than 0. So greater than or equal to 0, we're looking at brackets, -9 to 9. So you plug in -9 or 9 and the equals 0, plug in anything in between, and you're going to have something positive or greater than 0. So there's your domain for that function. Okay, and then root functions, we're going to, knowing domain help us with graphing. They give you some function capsules on pages 308 and 309 that show you the root functions when n is even and show you the root functions when n is odd. It's a good idea to go ahead and study those and be familiar with the shapes. But basically, when n is even, your root function is going to have a shape like this. Some starting point. When n is odd, it's going to have a shape like this. So when n is even, your domain, remember you're restricting your domain so that the radicand 0 or higher. When n is odd, your domain's -infinity to infinity. But knowing those basic shapes, knowing how they start, you can get your graphs by doing some stretching, shrinking, reflecting, all that good kind of stuff. All right, let's start with f of x equals square root of 9x plus 18. Now, I know what the domain is because we found it a few minutes ago. I know the domain was -2 to infinity. So I know that this thing starts at -2. And then I could always do an XY table and get more points. Okay, so I know at -2, I'm going to get 0. Let's see, at -1, I plug that in, I'm going to get 3. 0 is the square root of 18, so let's see, do I really want to do that? 1 is the square root of 27. 2 will give me the square root of 36, which is 6. That's probably enough. -2, 0, -1, 3, 2, 1, 2, 3, 4, 5, 6. So, that gives me an idea of what the graph looks like. But I could also use my transformations. Okay. F of x equals square root of 9x plus 18. I can factor out a 9. If you can factor inside, do so. Oops, factor out a 9, and I need my eraser. I started writing the 18. Oops. It's the 18 there. So factor out 9, you get x plus 2 in the parentheses. Then you can break that up. You got square root of 9 times square root of x plus 2. So you got 3 times the square root of x plus 2. So knowing that, I can start with the square root of x graph and then you apply my rules of transformations to get a different result. Okay, so let's say I start with square root of x. Okay, square root of x, I'm going to have 0, 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. Okay, so square root of x will look like this. Okay, and then I do the x plus 2. Let's change my color here. And I look at f of x equals square root of x plus 2. And this is going to tell me that it shifts left 2. So this point here goes over 2. 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 So that's f of x equals square root of x plus 2. I lost my pointer. Where did it go? There it is. Hard to see the orange. And then I'll go back to black for this one since it's already in black. And then f of x equals 3 times square root of x plus 2. Multiplying by that 3 gives me a vertical stretch by a factor of 3. Squeeze that in here, sorry. So you look at it, here you got 0, the y value 0 times 3 is still 0. Here the y value is 1 times 3 gives you 3. Here the y value is 2 times 3 gives you 6. And then like this one, the y value is 3 times 3 would give you 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, I miscounted. There we go. So yeah, if you had plugged in, if you had plugged in 3 earlier, 9 times 3 is 27 plus 18. Let's see. Did I think about that right? Oops, not 3. Sorry, 1, 2, 5, 6, 7. 9 times 7 is 63, plus 18 is 81. Square root of that is 9. So you would have gotten that point up there. So there's that vertical stretch by a factor of 3. So your rules of shifting, reflecting, stretching, shrinking, all that still apply to root functions. Okay, let's do this next one just with those rules. Okay, I've got f of x equals cube root of 8x minus 24. Okay, the key to doing these is to make sure to factor out what's inside, factor the insides, and see where that takes you. So I can factor out an 8. So I've got cube root of 8 times cube root of x minus 3. So I've got 2 times the cube root of x minus 3. Now remember, the domain for the odd index is negative infinity to infinity. But we are going to have still some shifting. So let me change colors here and let's step through how the shifting would look and all that. All right, starting with blue. F of x equals cube root of x. You have 0, 0. Cube root of 1 is 1. Cube root of 8. Oh, cube root of 8 is 2. So that goes up there. Negative 1, cube root of 8, negative 1 is negative 1. Cube root of negative 8 will be negative 2. Okay, so So your plain old cube root of x will look like this. Then when I draw this, you can see how the domain is negative infinity to infinity. Now, as soon as I subtract 3 inside there, that's going to give me a shift to the right. It's hard to decide on a color to use. Maybe I'll do red. That's going to shift right 3. So this point goes 1, 2, 3 to the right. This point, 1, 2, 3 to the right. This point, 1, 2, 3 to the right. This point, 1, 2, 3 to the right. And this point, 1, 2, 3 to the right. Okay, and then finally in black, we'll vertically stretch by that factor of 2. Okay, so 0, 0 stays put, because 0 times 2 is still 0. This point, the y value is 1 times 2, then give you y value of 2. This point, the y value is 2 times 2 is going to give you y value of 4. This point times y value is as y value of negative 1 times 2 is going to give you negative 2. And then this point has a y value of negative 2 times 2 is going to give you negative 4. So now it's nice and kind of wide now because of that vertical stretching. And there you go. So there's your final product. And if you go back and plug in x values, like if you plug in 3, 3 minus 3 is 0, cube root is 0, 0, times 2 is 0. If you plug in 4, 4 minus 3 is 1, cube root of 1 is 1, times 2 is 2. If you plug in 2, 2 minus 3 is negative 1, cube root of negative 1 is negative 1, times 2 is negative 2. So you can still do an xy table and get these results, but it really helps to know like where the function's graph going to be, generally what shape it's going to be, so that way you know that you've gotten enough points to really see what it looks like. All right, and one more. This one's tricky. This one's going to involve some reflecting. And with roots, it's a little bit tricky, so that's why I wanted to make sure to do this with you. We've got a function, f of x equals negative 4th root of 6 minus x. Okay, so one thing first. Inside, let's do a little factoring. Let's factor out a negative. And after you do that factoring out of a negative, you're going to have to use the negative and reflect across the y-axis before you shift it right 6 units. That's just something like if you see minus the x in here like this, know that you factor out the negative. You're going to reflect across the y-axis before you shift it. Just to be aware. All right, let's start with a different color. Let's start with f of x equals 4th root of x. Start there. 4th root is 0, 0. 4th root of 1 is 1. We could do 2, 3, 4. Those are all going to give us decimals, but you can do them if you want. You have to do like 16. So this thing's going to be kind of stretched like this way. It's going to be kind of narrow. Because if you do the fourth root of 16, you'll get 2. So this thing's going to be kind of laying low for quite a while right here. But anyhow, all right. So let's change color. You can go ahead and do the reflecting. That's going to reflect it across the y-axis. So then it's going to look like this. And then we can shift it to the right 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And earlier I had said we needed to get to 16, right? Yeah, 16. I could use -10. Yeah, it'd be nice to have a point to work with here. Extra point. Yeah, so -10, comma 2. Then you can see exactly where it's going to end up. So it's going to lay low for a while, like that. And then finally, I'll do black. Finally, got the negative outside, which reflects across the x-axis. So this point stays here, reflect across the x-axis, reflect across the x-axis, and you end up with this. Not easy to draw. It's so narrow, so gradual, it's hard to have that kind of control. But anyways, it goes that way. And there's your final graph. And if you want to, you can put it in your calculator and confirm. Let's see, y equals, we're looking at negative. And then we got 6 minus x raised to the 1/4 power. We get graph. And there you see it. 1, 2, 3, 4, 5, 6. And you see it's underneath going that way gradually. If you do your table, you do second graph, you see that at -10, you have the -2. And then when you get to 5, you have -1, and when you get to 6, you have 0. And those are the same ordered pairs we came up with after we did our reflecting and stretching and so forth. So there you have it. All right, so there's plenty of those to practice. Make sure you get as much practicing in as you can by hand with the graphing. You need to know how to do all this graphing stuff both by hand and with your calculator. So practice it both ways. All right, until I see you again, happy roots, happy powers.